right, this is chapter 6 on thermochemistry. We're going to start off with the beginning of the chapter, which is essentially a little background on what you need to know about energy. So, heat involves the transfer of energy between two objects due to a temperature difference. We call energy the capacity to do work or produce heat. The law of conservation of energy says that energy can be converted from one form to another, but cannot be created or destroyed. The sort of meaning of that is the total energy content of the universe is constant. Energy is something that we consider a state function, and a state function is a property that does not depend in any way on the system's past or future. It only depends on the present state. All right, so a state function is a property that does not depend in any way on the system's past or future, only the present state. The concepts of work and heat are not considered state functions because for them it does depend on what has happened beforehand. So let's talk a little bit more about energy, and specifically the different types of energy. So you can have potential energy, which is considered positional energy, and you can have kinetic energy, which is the energy due to the motion of the object. So the best way to sort of keep those two terms in mind is that kinetic energy involves moving. So if you consider going up a hill on a bike, there's energy being put into that motion. Potential energy up at the top, you have a lot of energy that is stored up that can then be converted back into kinetic energy on the way back down. Kinetic energy, the energy of motion, depends on the mass and velocity of the object. Okay, kids are screaming downstairs. All right, they've stopped screaming, so I'm going to take that as a good sign. The equation that I've given you there, so kinetic energy equals 1/2 the mass times the velocity squared. Chemical energy is the potential of a chemical substance to undergo a transformation through a chemical reaction or to transform other chemical substances. And when we're talking about chemical energy, there's some terms that come up that tend to be a bit of a sticking point for some people. So if we were to refer to the system, that would be the area of the universe that we're focusing on, like the experiment. If we refer to the surroundings, that is everything that is outside of the system. And the system and the surroundings together make up the universe. There are different types of chemical reactions that you can have. You can have an endothermic reaction. And in an endothermic reaction, there's a net absorption of energy or heat exchange by the system. And in this case, energy is a reactant. An example of an endothermic reaction would be baking soda and vinegar. When you mix them together, they actually get very cold to the touch. An exothermic reaction, however, is when you have a release of energy by the system, and energy is a product. And so one example could be that when you burn methane gas in the lab, the burner produces heat, and that is a exothermic reaction. Another example is light stick. So if you break a light stick, you start that chemical reaction, it gives off light, and that is also energy. Important to keep in mind that the energy gained by the surroundings must be equal to the energy lost. There are a couple of graphs that kind of help sum this up. So if we were going to look at a graph, here we have the direction of the reaction and how much chemical energy you have. If we were looking at an endothermic reaction, the reactants would have less chemical energy than the products because in an endothermic reaction, energy is absorbed. That's different than an exothermic reaction. In an exothermic reaction, the reactants are going to have more energy than the products because energy is released. And I like this one. It says endothermic reactions, I studied them before they were cool. That made me giggle too hard. All right, anyway, moving on. So here, let's take a little second here to see if we're following. Is freezing of water an endothermic or exothermic process, and why? So pause it and think about it. Okay, The freezing of water is an exothermic process because you must remove energy in order to slow the molecules down in order to form a solid. Let's take another practice. So we're going to go through, and I want you to think about the processes here, whether they are exothermic or endothermic, and explained why. And in these questions, the system is underlined in each example. All right, so for A, your hand, and we're saying your hand is the system, your hand gets cold when you touch ice. Is that endothermic or exothermic, and why? You should have said that it is exothermic, and that is because the heat energy leaves your hands and moves to the ice. Next one. The ice gets warmer when you touch it, and in this example, the ice is the system. So is that endothermic or exothermic? You should have said that that was endothermic, and that's because heat energy is flowing into the ice. Next one. Water boils in a kettle being heated on a stove. Water being the system here, is that endothermic or exothermic? You should have said that it was endothermic, and this is because the heat energy is flowing into the water in order to boil it. Next one. Water vapor condenses on a cold pipe. Is that endothermic or exothermic? It is exothermic. It's because the heat energy is leaving to condense the water from a gas to a liquid. Finally, ice cream melting. Is that endothermic or exothermic? And in this situation, the ice cream is the system. You should have said that it was endothermic, and that's because heat energy is flowing into the ice cream in order to melt it. Let's look at another one. Hydrogen gas and oxygen gas react violently to form water. Explain the following question. Which is lower in energy, a mixture of hydrogen and oxygen gases or water? Pause it and think about it. You should have said that water was lower in energy, and this is because a lot of energy was released in the process when the hydrogen and oxygen gases reacted, and you would get that cue by reading that hydrogen and oxygen gas reacts violently. So there is a violent reaction where water is released, so the products are going to be lower in energy. A couple more things to go through, and that involves the concept of energy and work. So just to sort of backtrack slightly, the study of energy and the conversions that it goes through is called thermodynamics. And oftentimes the law of conservation of energy is also called the first law of thermodynamics. And thermodynamic quantities consist of two parts. There's some type of number that gives the magnitude of the change, and there's also a sign that indicates the direction of the flow. So if we are looking at an equation to sum up the total energy that is going on within the system, when it says internal energy, that refers to the energy in the system alone. You could, and essentially the conversions that the system would be going through, the energy conversions within the system, the change in energy is going to equal Q plus W, where Q represents heat and W represents work. And those two things, the Q and the W, is what we're talking about when we say that they will give us information on the magnitude of the change and the direction of the flow. And again, we're talking about the flow of energy. So let me go a little bit farther here. We're talking about heat, and this is Q. The sign of Q is going to reflect what's going on in the system. In an endothermic process, Q will be positive. That means that heat is absorbed. In an exothermic process, Q will be negative, and that means that heat is released. Now when it comes to W, or work, that also gives us information about what's going on. If W is negative, that means that the system does work on the surroundings. And one example of that can be with gases. If a gas were to expand, so the gas is expanding into the surroundings, that's an example of work being done by the system on the surroundings. And in that situation, W is negative. If the surroundings do work on the system, then W would be positive. And one example of that, still going with gases, would be compression. So if the surroundings are compressing a gas, then the surroundings are doing work on the system, and in that situation, W is positive. So let's look at some examples. The problem says determine the sign of delta E for each of the following with the listed conditions. So let's start with A. In A, an endothermic process that performs work. In an endothermic process, Q is positive and W is negative when the system does work on the surroundings. So if work is greater than heat, then what will the sign be of delta E? Well, if work is greater than heat, then W is negative and Q is positive. And so since the work is greater, then delta E is going to be negative. The opposite of that, if Q is greater, and that's heat, if Q is greater, then delta E is going to be positive. For the next one, the work is done on a gas and the process is exothermic. So in this situation, Q is negative for an exothermic process and W is positive when the surroundings do work on the system. So for the first one, if work is greater than heat, that's Q is greater than, when work is greater than heat, that's W is greater than Q, then delta E will be positive. In the second situation, work is less than heat, so W is less than Q, and remember that Q is negative for an exothermic process, so delta E is going to be negative. Now, hang in there with these. I know that this part gets a little confusing. All you really need is a basic understanding of what Q would look like for endothermic versus exothermic, and what W stands for, and whether it's positive or negative depending on whether work is being done on the system or the system's doing work on the surroundings. And that would be it for the beginning of Chapter 6.